We are in chapter 4 where we are discussing bending. This is the 32nd session overall. Here we look at general eccentric loading. This is the roadmap we are following in the first 4 chapters, and we have reached session 32. Here we consider the case of general eccentric loading. It will be shown later on that such loading can be seen as equivalent to an axial load and moment about two perpendicular axes. We earlier considered an eccentric load applied on the vertical axis of symmetry. It was shown that such load is equivalent to an axial load acting on the centroid and a moment. This is a case of general eccentric loading. The load P is not applied to any axis of symmetry. It is at a distance a from the horizontal axis of symmetry and at a distance b from the vertical axis of symmetry. As earlier, let us consider two forces which are of equal magnitude applied at the point B as shown in this figure. Then the loading in figure 2 is statically equivalent to the loading in figure 1. Now this loading can be considered to be an axial force applied at B and a moment about the z-axis of magnitude Ba. Let us now consider two forces of magnitude P applied at the centroid. These forces are equal and opposite as shown. Then figure 3 is statically equivalent to figure 2 and also statically equivalent to figure 1. These three axial loads can be considered to be an axial force acting on the centroid and a moment about the y-axis of magnitude Pb. Again, figure 4 is statically equivalent to figure 3, 2 and figure 1. So, as earlier mentioned, an eccentric load P is statically equivalent to a load P acting on the centroid and two moments about two perpendicular axes. We discussed eccentric loading on the axis of symmetry, and the stresses were given using this expression for a tensile load P and a moment acting as shown. The moment caused compressive stresses on the top portion and tensile stress on the bottom portion. We'll now deal with two different moments about two perpendicular axes. As such, we relate the sign of the moment to the direction of the axis. The moment is considered positive if the direction of the moment vector, as shown here, aligns with the direction of the axis. Find the direction of the moment vector. We take the fingers of the right hand in the direction of the arrows of the moment, and then the thumb shows the direction of the moment vector. So in this case, the direction of the moment vector and the z direction coincide. So this moment will be considered as positive. So for the coordinate axis arrangement shown here and the direction of the load and the moment, the stress will be given by this expression. In this figure, we have added another moment about the y-axis. Now let us rotate this figure by 90 degrees counterclockwise. So AB, which was on the side, is now on the top. Now let us compare the moment about the y-axis to the moment here. The direction of the axis is the same. So this is the z-axis and this is the y-axis. Also, the direction of the moment is the same. However, the z-axis is oppositely directed. So compared to this case, which is given by this formula, we expect a sign change. So the stress due to moment about the y-axis is given by this term, which has a positive sign. Then check the sign physically. Due to this moment, there would be compression on the top and tension on the bottom. My here is positive since the moment vector for this moment aligns with the y direction. Z below the y-axis would be positive. So below the y-axis, we'll get a positive value for this term, which checks out with our physical understanding. For this portion, Z would be negative. Then this term would be negative as well. It checks out with our understanding of compression in this portion. Let us now look at the neutral axis. The neutral axis is the axis of zero stress. Like in the case of eccentric loading on the axis of symmetry, the neutral axis here will not coincide with the centroidal axis in the z direction. It is given by substituting 0 for sigma here, as in this expression. The neutral axis will be linear as before, but for the general case of loading, will not be parallel to any of the axis of symmetry. Here we investigate the arrangement of axes in general and pertaining to this formula. We'll follow sign convention as before. So if the moment vector aligns with the direction of the axis, then the moment is considered as positive. To investigate the arrangement of the axis and the stress formula, we considered this problem. So we have two different moments acting about two perpendicular axes. We'll find out the stresses at a section as shown here. Initially, we considered the arrangement of axes as the same as before. For this arrangement of axes, both the moments are positive. We can check physically the stresses that will be acting. Consider this quadrant. The tail of both these arrows fall in this quadrant. So a point A, which is part of this quadrant, will be subjected to tensile stresses due to both moments. Now consider this quadrant. The arrow heads due to both moments fall in this quadrant. So a point B would be subjected to compressive stresses due to both moments. We now use this formula to find out the stresses at A and B. At A, we get the stresses due to the moments as positive, and at B, we get the stresses due to the moments as negative. So the results of this formula aligns with our physical understanding. Here the z-axis is 90° counterclockwise to the y-axis. In this figure, we have kept the z-axis 90 degrees counterclockwise to the y-axis, but both axes has been rotated by 180 degrees. Now the moment about the y and z axis are both negative. We again use this formula to find the stresses at A and D. At A, we find the stress to be positive due to both moments, and at B, we find the stress due to is negative due to both moments. So this formula is applicable for this set of axes. In this case, we have taken the z-axis to be 90 degrees clockwise to the y-axis. Here we get mz to be negative, but my to be positive. If we use this formula, we do not get the right results. If we use this formula, we get the stress at A to be positive for both moments, and the stress at D to be negative for both moments. So this formula gives the correct results. As such, we can say that this formula is applicable when we take the z-axis to be 90 degrees counterclockwise to the y-axis. When dealing with problems, we have used this formula and kept the arrangement of the axis as mentioned. We see that the stress is given by this general formula for any arrangement of axes. It allows for both these cases. Here we have a problem of general eccentric loading. The load P whose magnitude is given acts at a distance from both axes of symmetry. We initially do not assign the axis. The distance of the load P from the axis of symmetry are given, and we can find the centroidal load and the moment that will act on the section. We'll use this formula, and as such, we'll consider the z-axis to be 90 degrees counterclockwise to the y-axis. We can further simplify the process of finding stresses by using the moment vector. We'll align the positive direction of the axis with the positive direction of the moment vector. So for this moment, this is the positive direction, and for this moment, this is the positive direction. We now have the positive directions of the axis, and as earlier mentioned, we choose the z-axis to be 90 degrees counterclockwise to the y-axis. Aligning the direction of the moment vector with the axis will mean that when we substitute mz and my. In this equation, it will always be positive. We consider a section ABCD. For this rectangular portion, we find out area, IZ and IY. We next substitute the values in this equation. Here P is negative, and as earlier mentioned, both mz and my will be positive based on the direction of the axis chosen. So here we have got an expression of sigma in terms of y and z. Consider the point D. At D, based on the axis chosen, both y and z are negative. So we substitute these values to get the stress at D. Similarly, we substitute z and y for the point C, get the stress sigma C, and z and y for point B to get the stress sigma B. Can do a brief check. For this quadrant, both arrows have their tails. So this quadrant will have positive stresses for both moments. So C would have positive stresses for both moments. And we can see that it has positive stresses. Now we have found out the stresses at D, C, and B. At A, Z is equal to minus 150 and Y is equal to 75. We input these values in the expression for sigma and thus obtain sigma A. We now have the stresses at the four corners of this cross section. In order to give the stress variation for the section, we need the position of the neutral axis. The neutral axis is a line of zero stress, so we substitute 0 here. This expression is a linear expression in y and z. Substituting z is equal to 0, we get y as minus 37.5, which is plotted here. At y is equal to 0, z is 75, which is plotted here. At z is equal to 150, y is 37.5. And at y is equal to minus 75, z is equal to minus 75. The stress variation has been plotted in 3 dimensions. This flat surface, ABCD, is surface of zero stress, and the neutral axis is on this surface. Positive stress is shown upwards and negative stress downwards. We have another case of general eccentric loading. 3 tensile forces are acting as shown. At a given section perpendicular to the axis, we are required to find out the stresses at the corners and also the neutral axis. As earlier, we do not use the axis initially, but we will use this equation so that the z-axis has to be 90 degrees counterclockwise to the y-axis. There will be a centroidal force and 2 moments acting. From the tensile forces, we can see that the moment about the vertical axis will be directed, as shown here. Also, from the tensile forces, we see that the moment about the horizontal axis will be directed as shown here. We align the positive direction of the moment vector with the axis. We then choose the z-axis 90 degrees counterclockwise to the y-axis. With the axis chosen, we can find Iy and Iz of this hollow section. We can also find the area. All the three forces are tensile, so at the centroid we get the force P as can be seen. We find the moment about the y-axis. These two forces will create a positive moment and this force will create a negative moment. The net moment will be positive. About the z-axis, these two forces will create a positive moment and this force will create a negative moment. The net moment again will be positive. We earlier obtained the parameters in this equation. So we obtained P, Mz, My and also A, Iz, Iy. So we substitute the values and we get an expression of sigma in terms of y and z. So now using the values of y and z, we can find stress at any point in a section. In this section, we have chosen the corners as C, B, E, F. Consider the point E. Y is minus 45 and Z is minus 75. We substitute these values to get the stress at E. At F, Y is negative, but Z is positive. We substitute the values to get the stress at F. At C, both Y and Z are positive, and we substitute the value to get the stress at C. Similarly with point B, we can physically check whether we have got the right answers. The tail of the two arrows fall in this quadrant in which F is a point. So we expect the stresses at F due to both moments to be positive. This is what we get, and the tensile stress at F is higher than the other points. The arrowheads of both the moments are directed in this quadrant of which D is a point. So for both moments, we expect the stresses to be negative at D. This is what we get, as we can see here. And the point D has the highest negative stress among the 4 points. We earlier obtained this expression of stress in terms of y and z. At the neutral axis, the stress is 0. So here we have equated this expression to 0. This is a linear equation in y and z. At y is equal to 45, we get z is equal to minus 29, which we have plotted here. At z is equal to minus 75, we get y is equal to minus 38.52, which we have plotted here. We have joined these 2 points by a straight line which represents the neutral axis. We can check the position of the neutral axis corresponding to the stresses that we obtained at the 4 points. At F, we got a relatively high positive stress. At D, we got a negative stress, but the magnitude is not high. At E, the stress is positive but nearly zero. At C, we have a fairly high positive stress. So, given the stresses at the 4 corners, we do expect the neutral axis to be somewhere in this position.